let's start with some questions. How is wastewater treated today? Which are the unit operations that can make wastewater clean enough to be safely discharged to water bodies or even reused for irrigation? First, we find the so-called pre-treatments. Screens are intended to remove coarse solids, wood, rags, cans, bottles. Sieves retain smaller-sized solids, ear tips, toilet water, wet wipes, and so on. Screenings and residues of sieving can be handled as urban wastes, but some can be used to extract cellulosic materials. Degritting and De-oiling units remove sandy sediments and floating greasy matter, but not settleable organics. Settleable sediments are removed in primary settling tanks and are collected as primary sludge. But the core of the wastewater treatment plant is the biological section, where bacterial biomass grows and performs several tasks such as oxidize biodegradable organics, oxidize ammonium to nitrates, reduce nitrates to gaseous nitrogen, biologically concentrate phosphorus in their cells. Biological systems can be based on suspended growth colonies, called flocks, that are dispersed as a suspension in the wastewater. The mixture is called mixed liquor and the process is called activated sludge. Attached growth, where bacteria grow in the form of a biological film attached to inert supports, generally made of plastic material. They can be retained in fixed bed reactors, but they can also be freely moving in the wastewater. In this case, the biological tank is called moving bed biofilm reactor. In hybrid systems, suspended growth and attached growth are in the same tank. For example, in the IFAS process, integrated fixed film and activated sludge. Whatever the type of process, bacteria need oxygen to perform most of their bioreactions. To provide oxygen, aeration systems are essential. Separation of bacterial colonies from treated wastewater takes place in secondary settling tanks. Since a couple of decades ago, micro and ultrafiltration membranes have been installed in many plants. The combination of activated sludge process and membranes is called membrane bioreactor, MBR. This combination provides a far more efficient solid-liquid separation. If solid-liquid separation is performed through settling tanks, filtration and disinfection are often required to meet stringent quality standards. In both cases, sludge is recycled back to the biological reactor, while a fraction is discharged as excess biological sludge. But all this may not be enough. Surfactants and trace contaminants, such as metabolites of pharmaceuticals or other contaminants of emerging concern, may be removed by adding advanced chemical oxidation processes and/or adsorption on activated carbon. The purified effluent can be further refined in constructed wetlands for filter depuration. Now, we must properly treat sludge, the byproduct extracted from primary and biological treatments. Sludge is a slurry with a flow rate 2 orders of magnitude lower than the incoming wastewater. Nevertheless, it has a water content of 97 to 99% and is rich in biodegradable and unbiodegradable organic compounds. Sludge treatments have two aims. First, reducing the amount of biodegradable compounds. This process is called biological stabilization. This step is essential to reduce the risk of unwanted fermentation and putrefaction processes, which produce bad-smelling compounds and favor the development of microbiological contamination. Anaerobic digestion is an effective process that also produces biogas from which we can recover energy. Second, reducing the water content, which means reducing its volumetric flow rate. Thickening and dewatering are the treatments that aim at reducing the water content. belt presses, centrifuges, and filter presses are the most widely used technologies. Once sludge is stabilized and dewatered, it can be used in agriculture, often after a further treatment called hygienization that will ensure the compliance with microbiological standards. Other routes, such as thermal treatments, including monoincineration or co-incineration. In Italy, about 1/4 of the total amount of sludge is still sent to landfill, a route that is going to be phased out in the next few years. This is the state-of-the-art of wastewater treatment, but upcoming innovations will turn these concepts upside down. For example, new processes and technologies will turn treatment plants from energy-consuming to energy-neutral or even net energy producers. Also, treated wastewater can be reclaimed for agricultural or industrial reuse. Solid residues and sludge will be considered raw materials for further transformation into useful products, rather than residues to get rid of. These are some of the current trends that will lead to the next generation of wastewater treatment plants.